This conference will now be recorded.
Today we continue with ensemble learning, and we will tackle gradient boosting. It's closely related to ADA boost that we did last time. It's still a boosting algorithm. To start with it, like ADA boost, if you remember, we fit additive models in a forward-oriented fashion. If you remember with ADA boost, like we take the dataset, we build a model, we see where we are not doing well. On these examples, we give them a higher weight and we fit another model, and we keep doing that. It's like we build different models. Each model is focusing more in a particular region of or particular samples of the data set. So each model will focus more on them, and then we have like a voting weight, like an average weighting system that determines the classification. So you remember ADA boost, I hope.
Yes.
Yeah.
So same in here with gradient boosting. And by the way, this is like one of the star algorithm in machine learning in both regression and classification. It's the algorithm that wins like most competitions when it comes to like tabular data. Tabular data, I mean by that not images or text, these kind of things. It's like when you have a matrix, like or a spreadsheet of information, like something like that. Table, and we have here features, a class here or a regression value, and we have multiple samples. This is what we mean by tabular data. So we have values here, or categorical things like colors, red, green, etc. So that's what we mean by tabular data. And this is like the star, or the state-of-the-art algorithm for this kind of problems. So each stage introduces a newly learned weak learner to compensate the previous learned weak learner. What do we mean, guys, by weak learner? Do you remember? Do you remember what we mean by weak learner?
It's the one who has most of the misclassification.
Sorry, can you repeat, please?
It's the model that gets the more misclassification.
Yeah, it doesn't perform well, but it has some good generalization. It generalizes well, but the performance are very low. So that's what is a weak learner. Like last time in ADA boost, what kind of weak learner do we use generally?
Tree. This is
what kind of tree?
Small.
Small, yeah.
Yes,
exactly. Small ones. What we call stumps. Here, it's more or less the same. We use small trees still. If we want to use decision trees, we can use anything else in gradient boosting, but decision trees are very common as well in here. So the focus of the new weak learner is in the gradient. In ADA boost, where did we focus when we built a new learner, a new model? Where did we focus?
Misclassification, like the one
the misclassified examples.
Yeah.
We focused in the misclassified examples and we gave them a higher weight. But here we will focus on the gradient, and you will see what we mean by the gradient after this.
That means the one who classify well?
No, still the bad classifications, but with a different perspective, from a different perspective. So suppose you have a regression model. So here we are looking at gradient boosting for regression, not for classification. And it's with a small tweak, we can generalize it for classification. So we want to use it for regression. Suppose you have a regression model F that performs well, but is not perfect. So we have for F, X1 is one sample. We found out that it is equal to 0.75. 0.75. But the real value is 0.6. So we have a small mistake here. And for fx2, a second example, we found out 0.3, but the real one is 0.45. It is decent, but not perfect. And we can have more cases. So you want to improve the model, but you can't modify it. What will you do? So here, any suggestions? So you have like this model that has been built. We want to make it better, but we can't modify it. We still keep it. It is not too bad, as you can see. It's close to the target values, but we want it to perform better. What shall we do, guys?
Combine them and put it.
What? Sorry? What shall we do?
Change the parameter.
What parameter? We have already built a model F, and we can't touch it. We don't know how it works inside.
Okay.
So we want like to improve it without modifying it. What do you think we can do?
Train it more on different data.
Yeah, this is a solution, but how we can combine them? Like we have already F. One way in gradient boosting is to look at the error. We look at the error and we try to correct the error by a new model, like here. So we can still build a model H that predicts the error and correct the output of the model F. So we have F, the original model, and we try to make a new model H. This H model will try to predict the error. And then we sum them up. So this plus the error, we predict the error, which is another regression, and we can make it better. Do you agree with this way? Do you agree with this?
Here is to add another
Yes, it's to add another model. So here what this model H, what is going to be learning? For example, in these cases, what is it going to learn? It's trying to predict the error. What error are we going to make in this case? So in here, what is the error in here? How much is it?
0.6.
No, the error is not 0.6.
See,
this is the real value,
75.
what we wanted to predict. This is what we predicted, and this is the real value that we wanted to predict. So the error is what?
0.75 minus 0.6?
Yeah, 0.15.
Yeah.
And same in here, 0.15. So we take this input and we try from it to predict the error. And same in here, we take this input and we try to predict the error. And once we predict the error, we just sum it up and we get the real, or what we want to have. Something like that. So we build H, which is the error, and we get the new value from this error. Okay? So to build H, we just need this. We compute the errors, which are y minus f. F is the output of the model. Y is the real value. This is what we used to call the class or the regression value, the last column. Y is here, is the last column. Here we have the features, and Y is here. So Y minus this is what we want to predict, to correct, or to make the model better. Do you agree with me so far? Do you agree with me so far, guys?
Yes.
Yes.
Okay, so H may fit approximately the error. So H might compensate a little bit and improve the model, which is good. So if F plus H is still not performing well, what shall we do now? So we are not satisfied by F plus H. What is the solution? It's written just in here. So just fit another model G that corrects H again. And we will have the final model will be F plus H plus G. And we keep correcting all the more errors. Do you still agree? Are you happy with this way?
It means we keep adding models till we get our target.
Exactly, until the error is as small as you want. We'll probably not get a zero error, but it will shrink till a minimum value. So we keep adding more models, and each model will correct the error. So this is like the general formalism. Are you happy with this, guys, so far?
So far, so good.
Perfect. And you can add as many models as you want. But this is, as you would expect, it's the simplest way. We are not going to do it that way. So in that case, well, we were going to see the loss function after. So why there is no gradient in here? We have just there is no gradient. We are just computing the error, fitting a model, doing the sum, and etc. There is no gradient yet. How is it related to the gradient? Just to remember the gradient descent. So it minimizes a function by moving in the opposite direction of the gradient. For example, here. So to minimize it, the minimum is this is in here. So we move to the opposite direction of the gradient. So here the gradient is that way. It means it is negative. So we move in the positive way. The gradient is negative because it's pointing downward. If it points outward to the upper direction, it means it's positive. If it points downward, it means it is negative. So we move this way, this direction. So we move the opposite direction of the gradient, to the opposite direction. So this is very simple, how we use the gradient like to optimize, to find the minimum of a function. So this is what we do with the gradient. If we want to minimize this, we take this value, which is, let's call this is theta, and we subtract from theta the value of the gradient multiplied by a constant. So this is the value of the gradient. The gradient is just the derivative of the cost function. We are optimizing this. Theta is the value that is inside here. The cost function is based on theta. Is equal. This is what we want to optimize. The loss function has theta inside of it. Equal theta plus etc. Has theta inside. So if we want to optimize it, we try to modify theta that is inside. And this is the gradient. The gradient is just what we call when we have a multiplied by x, and this is f of x. What is the gradient here? So you remember this is the equation of what? This is the equation of what?
Linear regression.
Or just a line?
Line, yeah.
Just a line, simple line. So its gradient is this value. A. So it has just one gradient because it's a line. The gradient always points toward this direction. At any point here, it's always the same. So this is the gradient. But when the function is more complex, like this one, for example, the gradient will be different from point to point. So this is how to compute it. We compute J. We compute the derivative of J. according to theta. So and we like change theta by a small amount related to the gradient. So this is just to move the gradient little by little. This is not a recall of what we did about the gradient descent before. So this rho here is just a small number, generally 0.1, for example. We multiply it by the gradient to know the direction, and we move a little bit towards the solution until we reach the solution. Are you happy with this? Are you happy with this, guys?
Sorry, that is not clear for me, I'm afraid. Sorry.
That's all right. That's okay. Only you or everybody?
I think everybody.
For me, I don't understand what's the purpose of this.
Okay. Okay.
this
Yeah,
function.
that's fine. So let's again do it second time. So we have this function, and we want to find its minimum. Anwar or Amal, or what would you do? What are you going to do? We want to find where is the minimum. The minimum is our solution line. We want to go there. What will you do? Say this function is x squared, just to take it in an example. This is x squared, fx equal x squared. What will you do to find the minimum?
Is it taking the minimum value
Of what?
We explore. We check some
You
value.
did that in high school, guys.
Yeah.
We use derivative.
Yes.
You did it in high school, not even at the uni, and all of you did it.
Derivative, I think.
Derivative.
That's, and what do we do with the derivative?
To find the minimum.
Yeah, but how we solve it, not the derivative, and we stop. The minimum of a function, if you remember, is derivative equals what?
Zero.
Zero.
Perfect. Amal remembers. Derivative equals 0. That is like what you did in your final high school exam. So it was like
yes, نقطة التماس or something like this. I don't know.
Yes,
like,
yeah.
When we
I don't find the wording in English,
the
but
minimum. It's the minimum of a function. Of this function, the minimum of this function is when the derivative equals 0. And if the derivative equals 0, it means how is the gradient? Why do, like, just to make it more intuitive, why is when the derivative equals 0, why when this derivative equals 0, it is a minimum? Why is this? Just look at the gradient. How is the gradient here?
It changed direction. It changed direction.
It is flat. It is 0.
Okay.
It is flat. It has no direction, actually. The gradient here has no direction.
No, I'm talking about going down and after up. So this is.
So the gradient here has this direction.
Yeah.
Do you agree with me? Then
yes.
This one has this direction. A little bit, it turns. This one has this direction. It is turning until it doesn't point to any direction.
0.
Yeah, it doesn't point to any direction. So this is the meaning of the gradient. Here it is pointing that way. It is in the opposite direction as this one. But here it is 0. That's why the minimum or the maximum, even the maximum, the gradient is 0, by the way. if a function has a maximum, the gradient will be also 0, not just the minimum. You remember this from high school.
Yeah.
So for example, if you have a function like this, the gradient in here and here will be 0, which is a derivative. Okay?
Yeah, the slope,
Yes,
the
yes.
slope of the curve. I think.
Exactly, it's the slope. So this is how we solve things with the gradients. But unfortunately, it's not easy to solve this function all the time. If we wanted, like if we could solve it, we can quickly get the gradient. The minimum. If we could solve it, we can quickly get to the minimum.
Yes,
But it is not easy to solve all the time. It's not that easy. Sometimes we can't solve it numerically or analytically. Sorry. Like I mean by analytically the way you used to solve it in high school. We have to solve it numerically by steps. So here what we do, we go here because this function is very hard to solve analytically. So we go here and we look at the gradient. Is it positive or negative? The gradient is easy to compute, but not solving it when the derivative equals 0. So we look at it here and we move a little bit. The gradient is pointing towards this direction. Okay, let's move towards this direction a little bit. We go here, we look again, and we go here. We keep doing it until we find that the gradient is 0. When it is 0 or close to 0, because sometimes it's very hard to find it exactly 0, but we are very close. Then we stop and we say we found the minimum. Okay? Are you happy now?
Okay.
Yes, yeah.
Yeah.
So this is how, like, we optimize something to reach its minimum. So here we are optimizing J by modifying X. This is X if you prefer. Theta is the variable, which is X. And J is my function, F. So we're trying to optimize it. This is the rate by the amount of change. So we don't want to change a lot, so we don't jump, because if, for example, let's draw it. If this gradient is high, so we might jump from here to here directly. And we don't want to do that. We want to move little by little until we reach here. So I don't want to keep swinging from here to here and coming back. So that's why we multiply it by a small number, rho. The rho number that we fix in the beginning. And we get the best, if you prefer, J. So this is just a recall of how the gradient works. So this is the loss function. This is the loss function that is used in the gradient boosted trees. In gradient boosting. So this is just, what is this? Can you tell me what is this formula? Y minus fx squared. Do you remember this? What does it represent? Y minus fx squared. What does it represent? How did we call it before? We used it before in linear regression and other stuffs.
Is the error, but like when we use a square to have the positive value.
Yeah, how did we call it?
I forgot, to be honest.
Simply the squared error.
Square.
That is the squared error. We use the squared error and what?
Absolute error.
Exactly. Yeah, these are very famous errors. The squared error and the absolute error.
Mhm.
One sometimes is called L1 and the other L2. So this is the L2 equivalent. So we have this. Let's look at this formula, the squared error. And we want to minimize this. This is my tree, the sum of the trees. So this is the output of the first tree, Li, depending on what L, the first tree. sorry, no, this is it's by example, sorry. It's by example. So we sum all the squared error of the examples. So we want to minimize this, because we want to minimize all the errors, not just one error. Okay? Okay or not okay?
But where is the square here? It's like
No, we don't have, still the square is inside. This is the L.
inside the L. Oh,
yeah, this is the L, the square
okay.
error.
Mm-hmm.
This is what we call the loss function. L is the loss function.
Okay.
So this is the derivative of J, which is this one, against Fx, against F. So this, we replace it, just replace it in here, still F. And if we derivate this, what will we do have? If we do the derivative of this, where is the square? This one. If we derivate this, and this is the variable, what will we have? This is our x. We derivate it against this. What is the result? So this is my variable. It is no longer a function like, because we derivate it against this. So it will be equal to what? 2 multiplied by, so these two go here. This is a constant. Y minus F, big F, x. And we keep this 2. So this goes and this go. What is the derivative of this? Can you tell me?
Y minus fx.
Exactly. Yeah, this is so simple.
Yeah.
Y minus fx. This is a derivative of this, and this is not a function in this derivation, because we are derivating it against it. So this is seen as the variable. If it was a function, the derivative would have been different. So this is the derivative of this. So we can interpret the residuals as negative gradient. So what are we doing here? It's exactly what we did with the gradient. The gradient we took, sorry, with the residuals. The residuals are the errors that we computed before. We took the difference and we tried to fit another model that compute this or predict this error. That's what we did before. Yes or no?
Yes.
So we did this. We computed an error. And now by derivating this J, which is the mean square error, or the, sorry, not the mean, it's just the square error. We got the same thing to optimize. So we got this value as the derivative, as the new value of that we are going to optimize over, that we are going to predict. So the derivative of the square error or the residuals are what we use, like the difference between the output and the expected output. F, this one. So in this case, these are equal. Do you agree with me? They are equal, no? Yes or no? Tell me, they are equal. This is the derivative that we computed. This is the derivative. Can you see it? And this is what we optimized before.
Yes.
They are equal. So in the case of the squared error, in the case of J equals the square error, these are equal. So in other words, we are exactly optimizing by doing this difference. We are optimizing the square error. When we do this, when we compute this, we are optimizing the square error, which is this J. the squared error of the output of the output minus the expected output minus the computed output. So we are optimizing this. They are equivalent. Okay. So for regression with square loss, do you agree with this? Residuals are equivalent to negative gradient. We have established this. Do you agree with it? Silence.
I think we lost here.
Yeah,
right now.
lost.
Yeah.
We lost. We are almost sorry. Because we find it like minus
Minus what?
the slide before.
Yeah, it is.
That you shown before.
Yeah.
Not this one. Yeah, this one.
Yeah, this is because we are doing the sum. This one, the derivative of this is f minus this. You agree with this with this line?
So far, yes. Oh,
And they are just here inverted, by the way.
I see.
And this is what we computed here, what we tried to optimize in the first place. This. In the beginning, the idea of optimizing or predicting the error. We use this.
Yes.
Yes. So this is just, they are of course equal. The first, in the first place, what we found, what we wanted to optimize, and the derivative of the squared error. So the derivative of the square error and the residuals are equal. That's what we mean. Are you still unhappy? Still. What is this?
You said negative or they are equals, like
The negative, because they are inverted. That's all. The negative
so
is
they are
because
not equal.
no, the negative is just because we inverted them.
Okay.
Negative this will be positive. So y minus f. Negative of this is y minus f. Yes or no?
Yes, it is.
Negative of
It
this.
is clear.
Yes, negative of this. It's just negative of this, which is the opposite, y minus f. That's all.
Yes.
Okay?
Mm-hmm.
So and this is what we wanted to optimize in the first place. Before talking about the gradient. This is the residual that we wanted to optimize, to correct.
Yes.
Okay. So, yeah. So in this case, the negative gradient of the square loss is equivalent to the residual. It's the same thing. It's the same thing. We saw it here.
Yes, yes.
It's the same thing.
Yes.
So fitting h to the residual is equivalent to fitting h to the negative gradient, because there it's the same thing. So if we create a model that will like h that predict the residuals, is the same as fitting h to the negative gradient, because they are the same. So update f based on the residual is also the same as update f based on the negative gradient, the same result. So we are actually updating our model using the gradient descent without realizing. In here, we are actually updating the model with gradient descent actually. but we don't realize it. It's just a special case, a very special case of gradient descent, this update here. When we create a new model based on this difference, which is h, and we do the sum again. We sum it up in here. We put it in here, so we can have a new y. So we are doing the gradient descent without realizing, and this gradient descent is just a specialized one, like a special case. So we are using gradient descent even with this small difference between the expected value and the real value. Are you still happy? Don't focus too much on this negative gradient. It's just here to see that they are equivalent. Using the negative gradient of the square loss or the residual is the same thing. Just to see the equivalence between the two.
Okay.
So you can see that they are they lead to the same result.
Yes.
So why do we bother then? Why do we bother? This is the same. Why do we bother of using gradient descent when the simple residuals are doing the same job? Can someone tell me? Can someone, and this is an open question, you can say anything. You're not expected to get the right answer anytime.
Can you repeat the question?
Why do we bother of seeing like the gradient, using the gradients when the residuals are simpler and they lead to the same result? Why do we bother with the gradients? The residuals are very simple and very intuitive to understand.
Residual is limited, no?
To what? But they are, you find them easier to understand. They are more intuitive.
Yes, true.
Yeah. But we say we just here prove that the gradient on the square loss is the same as the residuals. Why do we bother studying this gradient thing when we have the residuals and they are much easier?
We wanted to optimize the residuals in the first place.
Yes. But why? So why do we bother with the gradient?
Because with the gradient, I think we can find the minimum easily. It's like we don't have with the, for me, I don't know. It's like with the residual, we have to try many parameters. We cannot know. But with the residual, it's more clearer. No?
Not really. Not about the clarity. It's just another aspect.
Or maybe general. I don't know.
Yeah, they are more general.
Does it have to? Sorry.
Yes?
Does it have? Is it for the loss or something that you put before?
Yeah. Well, it's like going a level above to the meta level, what we are optimizing, and then by the derivative. If you remember just one thing, you remember this formula in physics. V. When you were in primary school, this is the formula of physics that we used to do. V equal what? Distance or whatever. Distance divided by time.
Time.
Yeah, time.
And then when we grow up, they tell us it is a lie. Something like that. It's not true. We use something different. V equal what? This by
Delta T.
Yeah.
Time. Yeah.
It's the derivative now. When we grow up, we use a derivative. The derivative of the distance by t, by time. And this is more general. You can compute v at any point, but this is just the average v. The average v. So here we are trying to find a general way, a more general way, in optimizing something different than just the square error. Here we are unknowingly optimizing the square error. Knowingly or unknowingly. We are when we use the residuals, we are like optimizing this square error. And this is like the proof. But when we use the gradients, we can change it. Maybe the square error is not the best thing. We can maybe use something different. So we end up with something slightly different than the residuals. Close to the residuals, but something that can give us better results. Some like residuals, but with some tweaking, some modified things. For example, here, this is just a summary. I should have put this slide before the other one. So this is for the regular square error. Start with an initial model F, calculate the gradient, the negative gradient, minus G, instead of the residual, which for the square error is the same. Fit a model H on the negative gradients, and then we update F on this negative gradients, which are the residuals, and we multiply it by this, by rho. In the normal case of the residuals, rho equal 1, what? 1, because we do always F plus the error. In the normal case of the residuals, rho equals 1, because we are summing the original function plus the H function, which is the one that computes the residuals. So far, so good? Tell me, Amal, Miriam, Anwar, please.
Can you repeat the last point, please?
Yeah, this is just the original function. It is what was when we use the residuals. We did F, the new F equal F plus H.
Yes.
So to make them equivalent, we multiply it by rho, but we just to make them equivalent, we put rho equal 1, so they can be equal with the old function. So this is for how the square error is equivalent to the residuals. When we update, we put rho equal 1. But we can modify this rho. It's something very simple, just to see how they compare. So what is this?
Square error, loss function.
Square error, perfect. This is the square error. Because we have now a new function that doesn't take the residual it takes something like a meta information on the residuals, which is a square error. Square error is like a special case. And this loss function can take the square error or something else. The residuals we can't modify them when we have the residuals. It's not something that is like dependent on something else, on another function. But this loss function, we can modify it to not use the residuals, but here we are using the derivative of the square function, of the square error, that take us to the residuals. Now, because we have the formula that says the derivative of the loss function by F. And this is exactly like the speed formula. Instead of L divided by F, which gives us something that like the residuals, we are using the derivative, and we can modify this L to have something different than the square error, the square loss. Why do we bother again? Because the square loss is not always good. It has a problem. But this is why we are introducing all of these headaches. It's because of the problem of the squared error. If we use simply the residuals, we will end with a problem. The residuals are bad with outliers. For example, here, the difference is very small. Again, the difference is very small here. A little bit higher, but still small. If this was an outlier, it means that a bad value that was badly measured. We have this in data. The difference is high. Yes or no?
Yeah.
The difference is very high. Correct. So the model that is here, sorry, just to mention one thing, we are not using pure decision trees. Decision trees output labels. They don't output numbers. we are using something called regression trees, which are like a modification on the decision trees. They are very similar, but with a small modification to have numbers instead of like labels. Okay?
Mhm.
So when we have this value that is big, too big, what happens? The model will focus on it more because the error here is huge. And the error here is very small. So this when we sum them, what we are optimizing is the sum of the errors. Yes or no? We are optimizing the sum of the errors. We want to reduce the sum to 0. So
Yes.
the model will try to improve this more and ignore this. And the outliers have this problem. The outliers have are always having some big values in their predictions. Instead of 1.7, instead of 5, we got 1.7, and this is an outlier. So the mean square error, as you can see, gave us a huge value here, a huge error. The error is even like higher than the difference, the small difference. And that's what we are trying to optimize. And the mean square error here is very bad with the outliers. So the model will try to focus in here because this produces a lot of error, and will ignore this. And it will just overfit. It will try so hard with this and ignore this that it is like trying to learn something that is false. An outlier is some values that are not well measured, that have problems in the measurement. Like when we collected the data set, we have made some error or something, unexplained phenomenon happened. And this is why we go through these headaches of using the gradient and formalizing the problem in like a more general way, so we can have something different than the mean square error, and not using the residuals. So we don't want to use the pure residuals. We want to use something different that gives better results. This is why we formalize the residuals in a more mathematical terms. So we can consider the absolute loss, which is this, instead of a square error, or the Haber loss, which is this. So the Haber loss, it's if the absolute value is small, then we use this square error. If the absolute value is too big, it means that the difference are too big, we use this. We use something very close to the absolute error. It's like a combination of the absolute error and the mean square error. You can see it more or less that way. So the Haber loss, for big values, we use something closely related to this, to the absolute error. And for small values, we use the square error. And you specify your delta here. You can specify what number you want to use for delta. So now, if we compare the square error, the square loss, the absolute loss, and the Haber loss. So the square loss is this. The absolute loss, you can see that it is not as severe as a square loss for outlier. And the Haber loss with delta equal 0.5 is even better. It's really curved in here. They are the same in here as the square loss, as you can see. But here, with delta equal 0.5, they don't go too far. So we won't give this more weight. We won't focus a lot on this outlier. Are you happy with this, guys? I know this is not very trivial, but just to get like the idea, why are we using something that is not like intuitive, and we are formalizing the problem more mathematically to be able to have like more like degree of freedom. We can use different loss functions. The square loss is the natural way, but it doesn't seem to be right. It is not good. So we are formalizing things mathematically to be able to use something like this or this. The absolute loss or the Haber loss. So the negative gradient of the absolute loss is simply this, sign. The sign of the difference. And the negative gradient of the Haber loss is this. It's the residual if we have small values, and the sign multiplied, as you can see, the sign multiplied by this delta for big values. So we can use different loss function. So here we are not going to use the residual, we are just going to use the sign. So f plus p rho, which is a number that you fix like 0.5, multiplied by the sign. If the sign is positive, it is a 1. If it is negative, it's -1. Plus or minus. And we sum it with here. So this is equivalent to using optimizing the absolute loss. So we are not using the residuals anymore here. H is not predicting the residuals. It doesn't sound right. Yes or no? It is not intuitive. We are not like summing the residual. Normally H, this value should be the residual. Should be what we have missed. But here we are like optimizing just by a little bit according to H, according to the sign of H, or the sign of the residual. We are using, if you say for the absolute loss, we are just looking at the sign of the residuals to make it like more intuitive. We are using the sign of the residual and modifying my f slightly based on the sign. If the residual is positive, we augment it a little bit. If it is negative, we reduce it. So it doesn't sound like right. Tell me, guys. I need your expression. It doesn't sound right. Does it sound right or not? It is not false. We are optimizing still. We are making it better. I move in by changing f. We are changing f a little bit. We are making f better. But normally, the residual should do better because we are moving f by something close to the right amount. But without using the residual, if we use, for example, the absolute loss, we are optimizing f just by a little bit, by the sign. We go to add to it 0.1 if rho equals 1, or minor, we reduce it by 0.1.
Yeah.
Still, we are doing better. It's because we are not fitting only one H. We are not fitting only one H. We are fitting multiple H's. H1, H2, H3, and each one of them will contribute just by a little bit. We are not like changing with the residual way. We don't have a row. We have row equal 1, and we change it by the whole thing. But here we change it by just slightly. So each decision tree we contribute just by a little bit. This way, we are going to fit correct things. We are going to fit more decision trees. And in practice, this does better. This does a better job. And mathematically, outliers will not influence it by too much, which is normally outliers. We are just taking the sign here. So outliers are not going to have a big impact because the sign will tell. And this will have like a slightly different outcome. Let's continue. I know it is not super intuitive to get it, but just to see where is the problem and how we are compensating it. So negative gradient pays less attention to outliers. Big values tend to generate more errors, and the model will focus more on them. Still, when using negative gradients, we need to choose a proper learning rate. So this can be like one of the things that we need to fix. So this is for classification, but before going to classification, what is happening? Let's go here first. What is happening here? What is happening in this case is that and the effect of this row is that we are not accelerating the learning. We don't want to accelerate the learning by too much. With this row, each new decision tree or model is going to influence F just by a tiny little bit. We don't want it to influence it by a lot, and the next model will influence, like, for example, if the first error is, say, 1 of the first level, the first model, then after this, when we correct it, we get an error of 0.1. And then the next error is 0.02. So clearly, guys, this model is doing most of the job. The error is 1. It's reducing, like, say, from a big error, from an error 10, say, to 1. So it's correcting 9. And then this model will correct 0.9 errors, say. It's correcting more. And this one, or less than this one. And this one will correct just a tiny little bit. You can see that each model is having, like each previous model is having a higher impact. Do you agree with this?
Lose time and the resource.
Not necessarily this, but like models are not equivalent. This one is more important than this one because this one is correcting a lot of errors. This one is correcting less, and this one is correcting just a tiny little bit. The error went from 0.1 to 0.02, so which is it's correcting 0.08. This one is correcting 0.9, and this one is correcting 9. So clearly, guys, this model here is having a bigger impact than these two because it's correcting most errors.
Yeah.
Do you agree with this?
Yes.
Yes.
It's intuitive. I'm trying to make things intuitive.
Yeah.
So it is like this model is having like a bigger impact than this, and this one is having even a bigger impact than this. So each model is having more impact than the previous one, and this is not really good for generalization. In generalization, we want more or less the models to have the same impact. We want all of them to contribute the same way. Otherwise, this model will take most of the influence, and because it's a decision tree, it is not necessarily going to generalize very well. Then we might not end up with a good generalization. So that's why we multiply it. We prefer to reduce the influence of each model. It's like the gradient. The gradient is pointing towards a direction with depending on the length of this. But we don't change the value by the whole gradient, but we multiply it by a small number like 0.1. So we don't go too far. So we limit the influence of each model. So we make them like having the same, more or less the same influence. And because of this, we don't want to use the mean square error as well. We use something that has like a small influence, like the absolute loss or the Haber loss here. F plus the output of the model multiplied by this row. And by this row, we can control how many trees we are going to use. We might be able to use more trees that way, a lot more trees. And generally in practice as well, it's not easy to understand, but in practice, what happens is the more trees we fit, the better the results, and it seems that it takes very long to overfit. In practice, let's see here. So here, value can slow down the learning. This row, the row value can slow down the learning if it is too small, and require adding more trees. So we need to have a good trade-off and finding the good row. And it is common for this row to have like small values, something between 0.1 to 0.3, even less smaller values than 0.1 are used. And this row has like this minimum. Sorry. No, it's not this what I wanted to say. I haven't wrote it, sorry. What I wanted to say is like the more trees we add with small rows, the more the results are better. And we don't quickly overfit. It takes very long to overfit. And this way, the different models will contribute more or less the same way because they have the same factor. We reduce their effect. They influence just a tiny little bit. So each model, like in here, model 1 plus this row model 2 plus again row model 3. So if model 2 corrects things by a lot, we still curve its influence. We let it influence just by a little bit. Maybe if we find out that it is still worth using model 2 here, because models can be the same. We don't know if maybe model 2 and model 3 can be the same. So we can still be able to use it. The algorithm will tell if we use model 3 equivalent to model 2 or not, if we want to use it more many times. So we keep doing the same thing until we stop. So this row will just mean that models will have like similar, more or less similar influence, but we will have a lot more models, not just 1 or 2 or 3. If row is big, equals 1, we will have less models. We will finish quickly. But if it is small, like 0.1, we will need more models. Do you agree with me here?
Yes.
I know it is not like, by the way, a lot of people struggle with understanding this. AdaBoost is very simple compared to here. That's why I wanted to like put AdaBoost first to get the overall like philosophy and then go in here. And you don't, believe me, you don't really need to understand it fully at this point. It's good if you get it fully, but it's not like mandatory to understand all of this, the intuition behind it. It is good if you can, but that's fine if you can for now. So you can, but you agree with me that this one, if we put it in here, we will end up with less models. But if row equals 0.1, we will end up with more models.
Many models.
Agree with me here?
Yes.
Yeah, yeah.
All of you. Amal.
Yes, yeah.
Perfect.
But Reda, I'm a bit confused in here. So do we need to do we need to use more trees in here, or is it better to use more trees?
That's the goal. We need to using more trees is generally better. It gives us better results and less overfitting. This is like the general idea.
Mm-hmm.
And in how what was observed in practice. The more trees we have, the less overfitting we have. This is.
So then it's better to have like a low value of
row.
Yeah, of row.
Yes, it's better to have less value, but your computational power will be impacting things. Maybe you don't want to wait for 3 days to compute your models.
Mm-hmm.
So it's like a trade-off. You need a good row, not too high for a good to avoid overfitting, but to avoid but not too low, so your computing resources will be able to do the job. So this is why we tend to find a good value for this row. Okay?
Okay.
Yes, okay.
And also it gives the chance for other models to find other ways of optimizing the error, because maybe one model is not doing a good optimization of the error, is not computing the error in a way that lets a good generalization. So we give like the chance to other models to modify this error more ways. More ways means a better generalization. We go here also. Yeah, adding more trees will slowly overfit, so it doesn't impact overfitting a lot. So keep adding trees until no improvements. So this is the improvements on gradient boosting. So keep adding trees until no improvement is made. And this is how when we stop. This is like there are proper algorithms and proper ways to stop it. So trees depth. Generally, in gradient boosting or JBM, gradient boosting models, we limit the tree to 4.8. It's higher than AdaBoost. We limit the tree to 4.8 because we need a little bit more precision. We are dealing with numbers, and like in AdaBoost, we have stumps, so that deals with the labels. So in this case, because we have numbers, we need a little bit bigger trees. So we go from 4 to 8, but we don't go beyond 8 generally. Sometimes even 3. We use 3 as well. So minimum improvement to loss. When we construct our trees, we add like more criteria on stopping. So if the loss does not improve beyond a certain rate, then no longer split the node of a tree. So trees have like more rules in splitting the nodes. In this case, it's not the regular decision trees, but here, or the ID3 or C4.5 or CART, these are the standard trees algorithms, but we add more rules to prevent like making the tree bigger. So if the tree like doesn't improve the loss, then we stop like splitting the nodes. Also, similarly to bagging, in gradient boosting, we can use randomly sampled sub-samples per iteration. So we can like make the trees less correlated, like in bagging in random forests. So we can use some aspects of bagging here. So the next tree will be like less correlated with the previous tree. But that's all what we use, just random subsampling. Okay, guys. So these are the improvements. Also, how we can like use it for classification. We just add a tweak. Classes are converted into vectors of probabilities, like in here. For example, if we have a sample with 3 classes, we have 3 classes A, B, C, and the sample X is labeled A. So X is a sample that has it's labeled to A. So this A will be encoded into a vector. 1, 0, 0. This is for A, B, C. So we convert it into probabilities because gradient boosting, you can see it works with numbers. It works with regression. So we convert classes into values. And for each class, for each value, we build a classifier. So we have like in here 3 classifiers. 1 for this, 1 for this, and 1 for this. And for each one of them, we do the same thing as we did for regression. It's like we need to find 1, so we fit in here for this class. So for each class, we fit a gradient boosted tree. For each class, we do it. Class for this, for this, for this, and we try to like predict the probability instead of a class, of a label. So we predict the probability. That is, for example, if it was 0.7, if, for example, the probability here was 0.7, of this model did this 0.7, 0.1, 0.1. So we have 3 models, 1 per class. So the residual here is how much? Simple. The residual here is how much? 0.3. It's just 0.3, the residual. If we use the residual method, the square error, we are going just to do the same thing what we did before with this. And we do it for each class. So it just means that we do the gradient based boosting method for all the classes. And we'll have like 3 Ys, not just 1 Y. Y1, Y2, and Y3. And for each one of them, we fit a decision trees with gradient boosting, and we predict probabilities. And we try to optimize these probabilities. That's all what we do for classification. Do you get it? Very simple, guys. Do you get it?
Yes, it is, yeah.
Perfect. This is very simple.
Rida, I have just one question. So Yes, it's just I saw that you put the size of depth of the tree this time. So what's the depth of the small trees that we using for ADA boost for stumps?
A stump is just size 1. We take only one variable.
1.
Yes, we call it. You can call it 1. Yeah. We do only one split.
Okay.
And here we can go from 4 to 8.
To 8, yeah.
We can
Okay.
take there's a number of variable in ADA boost. We take only one variable as a node, and in here in gradient boosting we take more, like 4 levels or up to 8. Sometimes we take just 3.
Okay.
So it's because we are dealing with numbers, we need a little bit more precision. So that's why we go a little bit more in terms of depth. Okay.
Yeah. Okay, thank you.
You can see that it's not easy to understand. I know this is not trivial at all, guys. You need to understand it by practice. The more you practice, the more you get why, like fitting more trees, and each tree, and because trees are not very good at generalization, or here they are general enough, and we want also to limit, to curb the effect of trees. And the more trees we have, like we saw in all the previous models, when we do ensembling, the more models we have, the better it is. And here is the same thing. We want to add this row to be able to fit more trees. And this tends to have a better accuracy and a better generalization. Well, not necessarily better accuracy always, but the generalization is surely there. It's better. And this is how we control the number of trees. We have other parameters also for the explicit number of trees as well. So now let's look at the XG boost. This is the implementation of the gradient boosting that is like super famous. That is the one that seems to like winning a lot of competitions. It stands for, it's an implementation. The gradient boosting trees are like these trees on steroids, but it's just the formalism. It's there how they are described. It's its description. XG boost is an implementation. It's like something that is a library that is ready to be used. And it stands for extreme gradient boosting. It introduces several improvements on the regular gradient boosting. So one major difference is the introduction of penalties and using more regularized trees. So it doesn't use like simple regular decision trees. It can find the best split in trees, and it does that statistically. So it looks at how, like, if we are improving this residuals or what we are, or the loss function, and see if the tree is like in a split, if it is improving or not. If it doesn't improve, it stops before like continuing. So it adds several like ways, several like heuristics in growing these trees. Plus, it has some engineering improvements to make things fast, very fast. It uses also what we call Dart to build the trees. It's like modifications to the decision trees, so we can build them in a more optimal way when we will group them together. Some hyperparameters in this XG boost. We have the number of estimators, which is the number of trees. The maximum depth, I think it is fixed by default to 3. Regularization, this is what it introduced some regularization. Regularization are L1 and L2 respectively, because the kind of trees that are used in XG boosts have like weights in the nodes. I don't really know how they are used, this weight, so we have this tree. And say these are the nodes. These are the nodes here. So there are weights inside these nodes to compute some final values. I haven't used them, but this seems what they do. Some final values. So we have here weights. That this is actually is learning, or this XG boost is learning. We have weights W's to be able to average some values W's. So these are just regularization alpha and beta and lambda, sorry, to like not let this weight go too far. So this XG boost is learning these weights, so it doesn't allow them to go too far. It's exactly like L1, which is the mean square error, or the square error, sorry, and L2 is the absolute value, and this is their sum. It's just to prevent the W's to go too far. So there is like some averaging inside, because the tree is more complex than the regular decision tree, and it has these parameters. So it introduced a number of improvements, a lot of improvements, which allows it to like outperform actually most algorithms, to be honest. With all of these improvements, it has like this regularization. It has when it stops splitting, it has it uses dart improvements. There is a proper paper, research paper that explains how this dart is working to build the tree. So there are like multiple improvements over the regular gradient descent, but it's like they are considered as small improvements at multiple levels, and this it makes this XGBoost one of the super models in machine learning. Are you happy, guys, with this explanation? I know it is not simple, and it is really not simple. So that's fine if you find yourself a little bit lost at some point. But what I want you guys is to get a general idea of this gradient boosting. Are you happy, guys, with these general ideas? Like the general idea is that we want to fit sequential models, each one correcting the previous one. Second, we don't want the one model to take all of to compute everything. We want more models to fit one next to each other. So that's why we have the row to curve a model. And also we use this derivative, or this kind of formalism of computing the gradient, because of the problems of the squared error. The squared error have an outlier problem, so it does overfit because of the outlier problem. So because of this, we use the gradient method. But at the end of the day, we are just trying to optimize an error in a way that doesn't overfit. That's what we want. We have multiple models, model 1, model 2, model 3, model 4, and we want to optimize the error in a way that does not overfit. Optimizing it in one way, like by one model, is not always good. So we want to optimize it just a little bit by this model, and then a little bit by this model, etc. And in practice, this gives better results. And then the next improvement by XGBoost is at multiple levels, to be honest. It's many things, many small things, like how the tree is growing, how to limit the tree, how to add the regularization, how to. For now, I would prefer that you don't understand everything that is going in this XGBoost. If you understood what I said before, that's already good. Are you happy with this explanation, guys? Are you happy with the essential, what we need to understand? Tell me what is the essential part that I want you to understand here. Tell me, guys. Anwar, tell me, please. What I want you to understand, what I just said that I want you to understand here. Tell me.
How it works? I mean.
Yeah, how it works, of course. But what is the essential things I just said?
That we want to minimize the error.
Exactly. We want sequentially to minimize the error, and we don't want
overfitting.
We want to prevent overfitting by allowing more models to be fitted. So that's why we introduced the row. That's the goal of the row. A row will allow like each model to contribute a little bit to the correction of the error, and not like to contribute to the maximum it can. And this prevents overfitting. So we add a model that will contribute a little bit to the correction. Another model will contribute again more to the correction, etc. So it will allow us to fit more models and then prevent overfitting. So this is point 2. Point 3, why do we use the gradient? Why do you use the gradients? Because of
small point is like small amount of.
No, this is the rho, the effect of rho, not the gradient. We use the gradient because of the problem of the residual. We said the residuals have problems with outliers.
Yes.
If we use residuals, which is the square error, has a problem with outliers. It gives outliers more say because outliers error is always high, and it makes things worse. It will overfit. So that's why we have this gradient formalism, and we try to compute the loss not by using the residual, but by using other functions like the derivative of or the gradient of the square of the absolute error or the Haber loss. These guys are more like or less sensitive to outliers. That's why we do this gradient formalism and we formalize everything mathematically. Okay? So these are just 3 points I want you to remember. What is the first one? First point. We are fitting, we are correcting the error sequentially. Each model corrects the error in a sequential way. Second point. We want each model to contribute just a little bit to the error.
To the error.
Correct the error. To prevent overfitting.
That's why we're using the rule. Yeah.
Yeah, so we can fit more models. Point 3, we use the gradient because residuals are not that good with outliers. And we want
Reda, could you please repeat why we use gradient?
Because the residuals, so we use either the gradient or the residuals.
Yes.
The residuals are not good with the outliers. They give them more say because the outliers are higher, have a high error. And the decision tree algorithm will focus a lot on them because it tries to correct the big errors. Because they contribute, the outliers contribute more to the error than the normal values. So we will overfit to them. The algorithm, the decision tree will struggle. We keep struggling, trying to correct something that is not essential, like the outliers. That's why we use a gradient to be able to find new ways of computing this something that is like a residual but has less shortcomings than the residuals, which is here the derivative of the absolute error or the Haber loss. They are very close to the residual actually. If we go to them, they look like residuals. They look like residuals. Residual is this value squared. So the derivative of this is the sign. So the residual is the difference, but here we take just the sign. So the big value and the small value are similar.
Yeah.
And here we are taking sometimes the residual, like in here it is a residual. And in big values, we don't take the residual. In small values, we take the residual. In big values, we don't take the residuals. We take this formula, which is lower than the residual. So here is to avoid the problem of outliers.
Big outlier.
That's why we use the gradient. It's to find ways that looks like residuals but have less problems than residuals. Otherwise, we don't have other ways. Like gradient will help us to go from a loss function to this, and this, to this and this, mathematically. So we keep the mathematical correction of the problem. Okay? Are you happy with these 3 points, guys? Do you get them? More or less. No, not necessarily at 100%, but you get these 3 points,
Yeah.
Sequentially fitting models.
Yeah.
We want to put as many models as we can, so we prevent overfitting. This is the introduction of the rho. And then the residuals are bad, and the gradient is what allows us to find other ways than residuals to correct our errors. So these are the 3 points I want you to remember in the gradient boosting. XGBoost is more like improvement at multiple aspects in this and how to make the model more robust. Okay, are you happy with? I know it is not easy, and this is fine. it's even hard for me, like it was very hard for me, like to understand everything. There is even another depth of understanding, but there is no point of going there now. So you understand, like more or less, the philosophy of gradient boosting.
Yes.
And it is really a superstar method, especially this XG boost implementation. Now I want you to quickly speak about another ensembling method. It's not as famous as bagging and boosting, but it exists. I just want you to know that it exists. It is called stacking. In bagging, what kind of method did we use? What algorithm was used in bagging? We explained in bagging. No, not this century.
We devise on multiple.
Random forest.
Random forest, yeah.
Yeah, this is a single model.
Yeah.
Random forest has a bagging plus some extra stuff.
Mm-hmm.
And then in boosting, what did we use? What did we talk about?
Decision trees.
No, decision trees is what is used. What models did we talk about?
In boosting.
Yeah, the first algorithm was add
boost.
boost. Yeah. First algorithm in boosting. And the second one is
gradient.
Yeah, gradient boosting. This is the second one. So we used ADA boost to introduce gradient boosting. And believe me, if you didn't introduce ADA boost, you will struggle more with the gradient boosting, because ADA boost set the scene of these sequential models. Now, the other family of ensemble learning is stacking. Stacking is very simple to understand, but it is not used that much. So it is an ensemble machine learning algorithm that learns how to best combine the predictions from multiple well-performing machine learning models. So in bagging, we took models that has high precision or high accuracy on training, but are bad in generalization. This is for bagging. In boosting, we did more or less the opposite. We took models that are generalized very well, but have a low accuracy on training. In stacking, we take very good models. We take models that perform very well, and we try to improve them. So we train multiple models. First, build a set S of models that perform well, like using SVM, like very good models. SVM, maybe possibly using KNN, even possibly using random forest as one model. So we use multiple models. And then we try to combine them. The algorithm build a model that combines the output of each model and learn the best way to improve it, to improve the overall performance. We call it meta model, something like that. So we have here the data set, and we have multiple learner. Model 1, it could be a random forest. Model 2 can be an XG boost model. Model 3 can be an SVM. So we have a neural network, etc. We have multiple models, but all are performing well. And we want to combine them to perform even better. So what we do, we get the output of all of them. We take this output and we train another learner. It can be anything, an SVM, but this is just one model. It takes all the outputs and try to get a new output that is better than the output at an individual level. It improves their performance. So this is stacking. Very simple, nothing like special about it. You train multiple models, you group them together, their output, and you have a new model that takes this output and try to make the output even better. It knows, for example, if, say we have, to give an example, a better example, we have this data set. It has, like, say, 100 samples. 100 samples. Say model 1 is performing very well in these samples. 10 first samples. Model 2 is doing very well in these samples. They are doing well with the other samples. Model 2 is doing well in all the other samples. But in these 10 samples, it's doing extremely well. Same for Model 1. It's doing well in the other samples. But in this 10 samples, it's doing perfectly well. So here, here, and here. And so on. This meta learner, this model here, goes here and finds out that Model 1 does very well in this kind of samples. Does very well here. When a sample is close to these numbers. It could be a KNN, for example. It says that this Model 1 does very well when the samples are around here, close to here. It says that Model 2 find out that Model 2 is doing very well when samples are close to here, to these samples, and so on. So it found how these models are doing at different portion of the space. So if we give it an example that is close to here, it automatically found out that it is not here. A new example is not necessarily existing in all data set on the training set, but it is close to here. It found out because this example is close to here, it found out that Model 1 is probably going to be the one doing the best. So it uses Model 1 to predict the example that is close to here. Another time, an example that is close to this 10 in here is going to come. This model found out in one training that examples that are around here, close to here, are better performed using this model, are better predicted by this model. So it takes the output of this model, and so on. Sometimes it can average. It found that an average of this model and this model is better than using just one model for certain example. It can do a lot of combinations, but this is what this meta learner is learning. It learns more how these models are performing and how to combine them, and it can improve even their accuracy further. Are you happy, guys, here with this explanation? It's not that complex. It's like you learn how the models are behaving. This model is learning the behavior of these models and how they are performing. It's like you, actually. It's like a data scientist that is trying to see what model is the best. But instead of taking only one, it learns how to average them or select one of them at certain cases and so on. Are you happy, guys, with this explanation? It's not very complex.
Okay.
Other guys?
Yeah.
Perfect. So any questions? I think we are done with machine classification or supervised learning, sorry. No, you are only 7 now. What happened to the others? Was it that annoying?
It's summertime.
Sorry?
It's summer, so maybe
They went for holiday, yeah.
Yeah.
Oh, I see. No, because we started with 12, I saw, but now 4 are left. So if it is summer, we can have a break if you want. Let me know. So guys, we are done.
Or maybe we can make this science at 11 or something like this.
Okay, no problem. We can discuss it by email to see the overall thing. No problem. So do you have any questions, guys? We have finished the chapter. We have seen a lot of things now. We have seen the linear regression, logistic regression, decision trees, KNN, naive Bayes, SVMs, and ensemble learning, like random forests, AdaBoost, gradient boosting. We are talking about stacking. So we have seen a lot of models. How do you feel about them? Do you feel comfortable more or less? Look how they want? Do you have a feel against these models or with these models?
Maybe we need to practice already.
Sorry?
Maybe we need to practice something.
Of course, you need to practice a lot.
Yeah.
But do you have any question or something about these models?
Yes, Reda. For stacking, so I take it we just take the best models and we use them, while previously,
Yeah.
for I think it was for was it for boosting or for we built models based on misclassified data. So we were building
Yes,
like
in
models.
boosting,
In
yeah,
boosting,
it's from
yeah.
misclassified data, and in bagging they are all different. They take different types of models. Bagging takes models that performs well on training but badly on testing, and improves the variance. Boosting, in the other hand, does the opposite. Takes models that generalize very well. We call them weak models. Models that generalize very well, but they have very bad accuracy, and improve the bias, improves this accuracy. They can even improve a little bit the variance. So they both take models that are not good from this particular point of view. But stacking takes very good models and try to improve them a little bit more. So they take their base models are all different. The three strategies have different ways of tackling, like of using the base models.
So are we dealing for boosting and bagging? Are we dealing with weak learner, and then for stacking is meta learner because we choosing already?
The meta learner is a last learner. For boosting, we are dealing with weak learners. Weak learners, it means that they have a high bias. They have a low accuracy.
Yeah.
For bagging, we are dealing with learners that have high variance. They don't generalize well. It's like they memorize the output, but they have a bad generalization. But they are complex models. So we average them to improve their generalization power. And it works. It works impressively well. Boosting the same takes like weak learners and stack them together, and it works impressively well. It's actually the top model, considered by many as the top model, especially the gradient boosting model, especially the XG boost. But stacking takes very good models like an SVM, like a random forest, like all of these well-performing model, and try like to improve them a little bit further. Try to improve, like to bring them together and add some improvement to the in overall. For example, if let's say that their accuracy, this accuracy is say 70%, this one is 75, this one is 60. So at least with stacking, we are expecting here to, if this is 75%, we are expecting here to get at least like 80%. It improves things a little bit. 70, sorry, my writing is awful here. So we are expecting it like by adding stacking like layer, a meta learner, where it takes the output, it can like combine them and improve the overall accuracy from like 75%, which is the best one here, to 80% by combining everything. So that is what we hope with stacking. Okay, guys?
Yes. Reda, how do we know which model we like in reality when we have like data and we're working on a project? How do we know which model we should use?
Yeah, good question, and there is no definitive answer. Generally,
try.
Sorry? Yeah, you have to try.
Many,
Machine learning is a trial and error practice. You have to try and see. But sometimes you can develop some intuition based on the data that you have, what model you want to try there. For example, if you have a regression problem where linear regression first didn't perform a good job, then gradient boosting is probably something that is going to do an excellent job. So you can have developed some sort of intuition For example, the next time I will give you like a table and what is each model, what it is good at. But you will always need to try them. For example, the SVM is excellent in NLP. And this is another chapter that we are going to work on next time. Linear SVM especially does surprisingly well with NLP. If you don't want, for example, to tweak your model a lot, like something like random forest it has barely any parameter, any hyperparameter to choose, except the number of trees. So this kind of model doesn't need fine tuning. So if you don't want to use fine tuning, you can use a random forest as a base learner or as a threshold, and you try to find models that does better than it. So in practice, you will have to try multiple ways. I will give you like more insight next time and where each model is good at, and try and you will develop this by experience. You cannot have like a definitive answer in like one session or 2 sessions. It's an experience task.
Nice. Yeah.
So I hope you are happy, guys. I know today's session was not very easy because it wasn't super intuitive, but you don't need it to get it like fully at 100%. Just these 3 points, if you get them, you are fine. And let's see how we can do the next sessions. I will get in touch by email.
Nice.